Okay, in this video I'm going to go over the in-class assignment from the energies lecture. This is the pendulum problem that we were doing. So in this problem, we're asked to calculate the potential energy and the kinetic energy at each of the positions of this swinging pendulum. And it may be useful to look at a pendulum first and think about where it's going the fastest and where it's going the slowest. So here's a swinging pendulum. And you'll notice that at the tops of each of these arcs, when it arcs up here, it comes to a stop, right? So that it can come back down. So that's probably where it's going the slowest. And then as it's swinging down, it's speeding up, speeding up, speeding up. And then as it's swinging up, it's slowing down, slowing down, slowing down until it comes to a stop. So at each of these peaks, it's going the slowest. Where is it going the fastest? Right in the middle here. So what do we know about kinetic energy? Well, we know that it's related to both mass and velocity. So if the velocity is greater, what do we know about the kinetic energy? We know that it also is greater. So what's the kinetic energy when the ball is completely at a stop? It should be 0. Where's the kinetic energy going to be the maximum of this pendulum? Where it's going the fastest, so down here. Now we can also say something about the potential energy of this pendulum. Now potential energy, gravitational potential energy, depends on the position. So the position from the Earth. So where is the pendulum the highest? Well, at the top, right, at these peaks. Where is the pendulum the lowest? Down here at the bottom. So where is the potential energy going to be the maximum? Up here at the top, where it's the furthest from the ground. And where is it going to be a minimum? Down here at the bottom, where it's closest to the ground. So keeping these aspects of the pendulum in mind, let's go back to our problem. So it asks us to calculate the potential and the kinetic energy at each of these positions. All right, and we're given a few things here. We're given a distance, and if we use this as our base level here, that's like right where it comes to the bottom. It means the bottom of the pendulum is right at our base level, and the bottom of the pendulum here is right at 15 centimeters up. That gives us a good starting point because that means that the potential energy when the pendulum's at its base level, it's at 0. So we can already fill in something down here. So we know that at position B, the pendulum is at the base level, so that means that our potential energy is 0 joules. And we didn't even have to do anything yet. We just set our base level there. All right, so our next task is let's figure out what the potential energy is at position A, right up here. So what do we know about this pendulum? We know, first off, that we have a mass that equals 2 kilograms. And we also know that we have a distance or a height of this pendulum, maximum height, of 15 centimeters. So I'm going to go ahead and I'm going to convert this 15 centimeters into meters because I know that I want my answer to be in joules, and that requires all of my measurements to be in standard SI units. So I'm going to multiply this by a conversion factor. I want centimeters on the bottom, meters on the top. Now there's 100 centimeters in 1 meter. The centimeters are going to cancel out, divide through by 100, and end up with 0.15 meters. All right, so now I have a mass and I have a height. What else do I need to know to calculate the potential energy? Well, I also need to know how much this ball weighs, or I need to know the force of gravity that's acting on this ball, which also is the same as the weight. And that is equal to the mass times the acceleration due to gravity, which I can use because I'm doing the force times the force of gravity. I can use the acceleration due to gravity. So the weight of this pendulum is 2 kilograms times the acceleration due to gravity, approximately 10 meters per second squared. So we get approximately 20 newtons for the weight. So now let's look at our relationship for potential energy. Potential energy relies both on the weight and the height. Now, something I'd like you to always note here is that the weight, this is a force, right? And the height over here, this is a distance. So this is a force times distance. Do we know another relationship that calculates something with a force times distance? That would be work. Okay, in the case here of our potential energy, we have a weight of 20 newtons, and we have a height of 0.15 meters. And if I calculate that out, it's going to be 3 newtons times meters, and newtons times meters is a joule. So this is 3 joules. So this is what my potential energy is at position A, 3 joules. All right, so let's look at this diagram over here. And at the top over here, we're at 15 centimeters. And then if we look over here, position C, we're also at 15 centimeters. So our height is still the same at both of these positions. Has the mass of the pendulum changed? No. So the weight is the same. The height and the weight is the same. So that must mean that this relationship that we did down here, potential energy, weight times height, the weight didn't change, the height didn't change, so this doesn't change either. So that means that the position at position C, it's also 3 joules. Now let's think about our kinetic energy. Now the kinetic energy is going to be increasing as the potential energy is decreasing. And as the potential energy decreases, kinetic energy should be increasing. And over here, as potential energy is increasing, kinetic energy should be decreasing. Where is kinetic energy at minimum? Well, where the velocity is a minimum. So down on each of these 2 points here, velocity is at 0. So what must our kinetic energy be? It must be 0. If we have a velocity of 0, we have a kinetic energy of 0. So these 2 positions, we know that the velocity is 0, our kinetic energy is also 0. Now if we look at this, we look at, well, we have potential energy and we have kinetic energy. So now we can calculate a total energy. The total energy of this whole thing is potential energy plus kinetic energy, so 3 joules. And if energy is conserved through this whole system, which it must be due to the law of conservation of energy, the total energy must be the same at position B and position C as well. Let's check it at position C. 3 plus 0 equals 3 joules. Perfect. So what must our kinetic energy be at position B? It must be 3 joules. Or we can take this as our total energy and subtract out our potential energy, so 3 minus 0 joules, and we're left with 3 joules. So you just have to remember that in this case, when we're talking about conservation of energy, the total energy equals our potential energy plus that kinetic energy. And if you want to solve for your kinetic energy, you can rearrange this equation so that kinetic energy equals your total energy minus your potential energy. So halfway between them, the energy is going to also be halfway between. So you're going to have half of your potential energy and you're going to have half kinetic energy. And the total energy still needs to add up to be 3. So half of the potential, half of the energy being potential is 1.5, and half of the energy being kinetic is also 1.5. 1.5 plus 1.5 equals 3. Okay, so that was the end of the in-class assignment. But let's take this to one step further. How fast is the pendulum going at the bottom of its swing? So we can use some of the stuff that we already calculated over here. We know that the kinetic energy of the pendulum at the bottom of its swing is 3 joules, based on our previous calculations. We also have a relationship that relates kinetic energy to the velocity of the motion of the object. So kinetic energy equals 1/2 mv squared. So we can go ahead and we can rearrange this equation. And I did this in class, and I want to show you again. So I'm going to multiply both sides by 2. And the reason I'm doing that is I want to get rid of this 2 on the bottom there. So 2 divided by 2 is now it's gone. Now I'm going to divide both sides by m. And that's m divided by m. That gets rid of my mass. So I'll divide this side by m. And then finally, because I have got this squared here, I'm going to take the square root of this side and take the square root of this side to get rid of that squared. So that gets rid of this squared. Square root divided by gets rid of that square root. So if I simplify this out, and now I just have the kinetic energy all over the mass times 2 equals my velocity. And this is the whole thing is under the square root sign over here. So now I can calculate my velocity if I know both my kinetic energy and the mass. Let's see, do we know the mass of the pendulum? We do. It's 2 kilograms. So my velocity is going to equal the square root of 2 times my kinetic energy, which is 3 joules, all over the mass of 2 kilograms. So this is the square root of 3. And what are my units here? Well, everything's under square root, so it's joules per kilogram, which doesn't really look like a velocity yet. So let's take a look at these units here. So the units are in the square root as well as the number. So we have a square root of joules over kilograms. We can break the joules down into newtons times meters. So newtons times meters all over kilograms. So we can break this down even further because we know that newtons is kilograms times meters per second squared. And then times meters, we still have that meters up there, all over kilograms. Continue out this. So here now we can see that the kilograms are canceling out. We can multiply this meters through here so that we've got a square root of meters squared per second squared. And if we get rid of that square root and get rid of those squares, we're left with just meters per second. So up here, take the square root of 3 joules per kilogram, end up with something like 1.7 then meters per second, which is a velocity measurement. So that is how fast, 1.7 meters per second, how fast the pendulum is going at the bottom of its swing at point B.